This is going to be a talk about, as you see, bisimulation characterization theorem for hybrid logic, hybrid propositional logic, and it's based on a recent research by these 5 people. And these 5 people are somehow related to these universities. It's not a bijective map. It's not a map either way, but there is a relation. Right. So without further ado, oh no, not without further ado, because I need to, how do I, okay, maybe I need, click. Oh, I just click. Okay. Oh, and then it works. All right. So what's hybrid logic? Hybrid logic is a mixture of a modal logic, sort of standard modal logic, and bits and pieces of classical logic, first order logic. So the idea is you have the modal part to talk about modal stuff as usual. By saying as usual, I mean you have Kripke frames as you'd expect as the standard semantics. But on top of that, you also have a way of talking about Kripke frames themselves. So you can talk about points in Kripke frames and about the accessibility relations and such things in the same language. So this is why they're called hybrid, because it's a hybrid between a modal part and the, say, first order part. Or restricted first order part. So to be more specific, you have the vocabulary is, you know, the standard modal vocabulary up to here, and then you also have world variables, which will here be represented by X, Y, Z, blah blah blah. And you may have nominals. It's not necessary. Maybe you have no nominals, but you can have nominals. Nominals are just constant naming points in Kripke frames. So it's like first order constants, nothing special. And then you have, in the typical case, you have these 2 operators. This is sometimes you call it store, sometimes you call it current state binder. The meaning of this is at the current state phi. So at the point of evaluation phi. That is the operator that says at state W psi. Why do I have psi here and phi everywhere else? I don't know, but anyway. So, and this W can be a world variable, or it can be a nominal. If you have nominals, doesn't matter. And then sometimes you also add on top of it an existential quantifier, which is just your plain old existential quantifier from first order logic at X phi, which here is interpreted at the point X phi holds. All right. So this is the vocabulary. And the semantics is as you'd expect. So up to here, I think on this slide, I just have the standard modal part, which is just as you'd expect for a modal logic. This is all usual Kripke frame semantics. And then for the hybrid stuff, you add the clauses that you'd expect from the definitions. I mean, from the intuitions, let's say, about those operators. And so this new is a valuation, a first order valuation. So you map world variables to worlds. And M is a point in the frame. So of course, such things makes N true if the state of evaluation is the state named by X. Well, that's the same for the world variable. Then this is at current state phi. So you can imagine what the I mean, you can easily write down the condition if you just think of it, what it should mean. So, and the way I wrote it here is just the X variant of the valuation that maps X to M at M makes phi true. So, so this is all what you'd expect. And then you have similar clauses for the at operator, here for the nominal, here for a variable, and for the existential quantifier. So it's all what you normally expect of a hybrid logic. Right. Now, as in the modal case, we also have a standard translation. So as you know from modal logic, there is this standard translation that translates modal formulas to, or modal sentences to first order formulas. And this is an extension of that. And again, up to here, you have the standard modal translation. So notice, oh, by the way, notice that bit here. What it does is standard translation of a world variable W at the point X, is just the equality between W and X. So this wavy equality is the equality from the language, and the usual equality is just the plain old identity of objects. And this, if you remember that, and you put it together with this, then you will easily see that when you have this at and world variables, then you can mimic identity in your language. Because at yx, what would the standard translation be? Well, that would be x where y equals x. So in that way, your standard translation recovers identity, and then the standard translation of the existential quantifier is just the existentially quantified standard translation at another point. But then note that this immediately implies that if you have both the existential quantifier and, the existential quantifier and at, then you're back at classical logic. Then you have full force of classical logic. But this will show up later. But it's not it's not that important at this point. Okay, so what do we want? Well, we set out to prove some form of characterization of this notion of or rather. Well, okay, so all right, we have a hybrid logic, we have the standard translation, so we have some formulas which are standard translations of hybrid sentences, hybrid formulas. We want to go back, of course, yeah. So we want to have a characterization for a situation when you look at an arbitrary first order formula and you then wonder whether it is equivalent to a translation of a hybrid formula. So we want a characterization of that sort. Of course, bisimulations come to mind because we have that characterization for model formulae, and that comes from Van Bentem when? In early 80s, perhaps? He proved it? Yeah, all right. Anyway, so several centuries ago, Van Bentem proved the characterization. And so would be nice to have a similar characterization for hybrid logic, except that, let me see if okay, all right. So let's first look at what I'm sure most of you, if not all, are familiar with bisimulations, but let's just have a very simple example, which actually goes back to where I believe by the notion of bisimulation comes from, which is a bisimulation between finite automata. Here you have a finite state machine, an indeterministic finite state machine and the deterministic finite state machine, and they happen to be equivalent to one another. And this EPSI here is the empty word translation, so transition, sorry. So it's all indeterminism of that automaton comes from this empty word transition. And the bisimulation here is the relation indicated by those red dashed lines. And the idea here is whenever you have a computation path in one of these automata, let's say the upper one, then you will have a corresponding computation path in the lower automaton with the property that if you start at some pair of states, say you're at the initial state here, at the initial state here, and then you make a transition, then whenever you make a transition here and you make a transition here, then the states that you end up at are also related. That's it. That's the idea. This is really what it is. And it's easy to see, it just takes 3 minutes maybe to convince ourselves that this is really a bisimulation, that I mean in the sense that every computation path in one automaton corresponds to another to a computation path in the other automaton, and if and importantly, a word is accepted by this one if and only if a word is accepted by that one. So that's it. But there are things here that are not captured by this. So for example, say if you're at an initial state here, then the only state bisimilar to that state is the initial state. Yeah, but then you may make an empty word transition to some other state, and here you can't do anything. You have to stay at this state. So, for instance, for example, say you don't know how you began. But I tell you that here you are at this state, and there you're at the corresponding bisimilar state up there, the red one. Yeah. Well, where do you come from? You don't know. You don't know. You know that they are equivalent in a good sense, but you don't really know where you come from. And now, if you think about this in a hybrid logic way, you will see that this may be a problem, because so you can of course think of this as some sort of Kripke frame. Well, you have, in fact, here you have 3 accessibility relations. Yeah, there's 0 transition, 1 transition, and the empty word transition, which is identity in that automaton. But I didn't put the names on the states for a reason, because if you have names, then you'll see that things get wrong here. If you call this A and you call that A and they correspond to one another, well, then this can't correspond to this red up there because it won't be called A. And this is the problem with nominals, for example. This is a similar problem you encounter if you have the down arrow, the what you might call them, the binder, yeah, the binder, yes. And same for at. You will have a problem. There are different kinds of problems with these, but this is just an illustration. It's meant to be an illustration. So something has to be done. All right, what? Before I go to that, here's a list of existing results on bisimulation characterizations, because some results exist. I'm not sure, maybe there are more, but as far as we could find, these are the only relevant ones. So of course it's there is a basic Van Bentem result that characterizes, let's say, the empty, you can think of this as an empty hybrid signature, so only modalities, nothing else. There's a result by Orestes, Blackburn, and Marx that characterizes the language with at and the binder, and possibly nominals. It may or may not have nominals, but both are characterized. There is a notion of omega bisimulation there for this characterization. It will play a role because this is really the notion that we will work with some, how do I say? Attempt to say inessential modifications, but perhaps not so inessential, some modifications. Tenkate in his PhD proves something similar for the language with at, different notion of bisimulation, doesn't really matter. And then, I mean, it does matter, but we will not use it. Hodgkins and Tahiri proves a similar characterization for the language with the binder only. They use the notion of quasi-injective bisimulations, which are, let's say, bit like bijections, but not quite. That doesn't really, like injections, let's say, injections on the generated parts of. Again, it doesn't really matter for us what they are. What matters is that they were able to characterize, to obtain a characterization with respect to these quasi-injective bisimulations for the language with the state binder, but without nominals. With nominals, it breaks down. The method breaks down, and possibly even there is, well, I don't know about whether the result breaks down, but the method certainly does. Okay, so so we wanted to do something. Well, so it was, the whole work was really motivated mainly by the open question about the nominals. So it's quite funny how it started very small. Yeah, we wanted to get something for the language with the state binder and current state binder and the nominals. And then step by step, we realized that we can get a characterization, sort of a characterization for all the interesting fragments. And so our, okay, before I go into that, this is a sort of quick summary of the existing results for the fragments, for interesting fragments. For there are really 12 interesting fragments because, well, we have 4 things. So down arrow at existential quantifier and the nominals should be 16, but because existential quantifier implies down arrow, we go down to 12. So there are 12, and they are more or less summarized here because each of these cases, this, and that, has 2 variants with nominals, without nominals. So it summarizes the existing results. So, and we have 2 big unknowns. So this wasn't known, and that wasn't known. These, as I said, both this and the full signature, they amount to first order logic. So maybe this characterization, we do get characterizations, but they're not very interesting because, well, why would we want to characterize first order logic? That's been characterized as far as I know. Okay, so right, so now technical notions. And I think in the interest of time, I just jump over them quickly. So what we have is this. At the basic level, we work with relations that take 2 parameters, that k and n. K counts Okay, so if you think about the bisimulation in a sort of computational sequential way, is you know that the standard way of thinking is oh, we were at this well, I need both hands. We were at these states, then we moved to this state here, to that state there, and they are still bisimilar. And then we went further, and they are still bisimilar. In the standard form of bisimulation, you don't remember where you came from, but we do. And K counts how many steps we remember. N just counts the modal depth of the formula that we are that we are looking at. So so we have these two parameters, and then everything else is well, it's not really that surprising when you think about it and you start writing down the conditions. You will come up with the conditions. Well, first of all, those the propositional and the forth and back condition, they come they come directly from the usual conditions for bisimulations in model case. There's nothing special about them. For the world variables, you just do what you need to do. It really is natural when you think about it. So this is our basic case. And now we want to add, all right, so far we have a notion of a bisimulation that remembers k steps back for modal formulas, possibly with world variables. All right. And now we want to extend the signature. But what we do, well, we just add something to this to the language, maybe the binder, maybe at, maybe nominals, whatnot. So we want to have conditions that would correspond to these additions one-to-one. So we add one ingredient to the language, we add one condition to our notion of bisimulation. And indeed we do have such things. So I also, this is technical, doesn't really matter. What you have is you have a condition for adding nominals, you have a condition for adding binders, you have two conditions for at, because you want a condition for adding at with a variable and adding at with a nominal. Because you can imagine a language where you have at, but you don't have a nominal, so you want then to add the condition, but not for the nominals, the condition for variables only. And then the existential quantifier, which splits into two conditions, a fourth condition and the back condition. And that's natural, simply because it's a universal modality. The existential quantifier you can think of as a universal modality. So, so you have a corresponding condition. Okay, so this is our what I will call a hybrid signature. It can, it's a subset of this. For each subset, we of course have a corresponding. All right, so this is just that was the basic bisimulations. Now we have an extended bisimulation. You know what to do, yeah. You have ingredients in the language. You have conditions. Add the conditions. You know what you know what to do. And then okay, let's think about how these bisimulations are organized. So there is one important ingredient that I didn't talk about, and this is that red thing that I call extendability. Extendability, I think it was, or the storage rule. The idea here is this: so the vertical lines, just in the vertically, it's just that the modal degree of the formula grows. So say you start with 0, and then you go one more and one more and one more. At the end of the row, you just have the union of everything that was before. So nothing really special happens here for each case. So here here you will, so Z0, that one here, that would be the basic model by simulation. No memory, but arbitrary model depth. And then you increase the depth, and so, sorry, you increase the storage, the amount of memory, yeah, how many steps you remember, you go down, and you could have a situation where you have all the horizontal lines, but you don't have the connection between them. We want to connect them because we want to somehow preserve the previous bisimulation at the next stage where we go, we add one more memory cell if you want. How do we do it? Well, we just add what I already called the extendability condition, which is fairly natural too. So what is it? It just says if this tuple, remember this is a k tuple and this is an element, so this is k plus 1 elements. This is also k plus 1 elements. They were related. For technical reasons, they were related for the I-1 depth. Then we want to say that our k plus 1th relation will relate what? Will relate the concatenation of what we had before with that u, with this u here added at the end. And same here. And another way of thinking about it is that this string, this sequence of points is a valuation for the first k variables, and this guy here is the evaluation point. So then if you have this, then you want to be able to do this. Yeah, if we had stuff true at u, and if and only if that stuff was true at u prime, with the valuation of that length, then you want to be able to say, well, all right, so add this to that valuation and then repeat the evaluation point, and the same should be the case. That's the idea. Okay, so this gives us the vertical lines. The way to think about it may be, I mean, this is not a perfect analogy. Well, I mean, if it is an analogy, then it's not perfect, I suppose. Anyway, the way I think about it is, like, if you have all the horizontal lines, this is like elementary equivalence for first order case. But if you also have the verticals, so you have all the omegas, all the omegas of this z omega, this is like an omega back and forth equivalence, stronger. That's the way. Again, I repeat, this is just an analogy, but it was, at least for me, it was a useful analogy. Okay, yeah, so this just repeats what I've just said, so I don't need to spend time on this slide. Then what? Then we have, then we are pretty much at the end. So we need a lemma. We need another lemma. So right, and then we need this. This is the most important ingredient. And I tell you about the proof, just 3 words. It's really, I should call it the Lindström-Badia lemma because, well, I mean, technique comes from Lindström, but the idea of the lemma comes from Guillermo. Idea of using it for this type of for this type of thing. So we want to prove. Okay, this HTTP. What is this HTTP? It's not the protocol. It is. You think about this as the complete type on U restricted to the formulas that are translations. So you throw in everything that is true at U, but not all the formulas, but only the formulas that happen to be translations of hybrid logic formulas. And we want to prove this equality. Now, this inclusion from right to left is trivial because look what we are summing over. We're summing over models of phi. So it stands to reason that models of phi happen to be models of phi. The other inclusion is important. And to prove the other inclusion, we do the Lindstrom trick. So here are the ingredients. Suppose we reason by contradiction, just like in Lindstrom classical paper. We reason by contradiction. Suppose we have M1 and M2 such that this phi, remember phi, we assume is invariant under omega by simulations. Suppose we have two models, one that makes it true, one makes its negation true. Well, at a point, I should mention, but that's good enough anyway. It's hand waving. Make the languages disjoint. On top of that, rewrite over everything that you need to that you need to do. On top of that, write a huge first-order theory that that states the our conditions for bisimulations in a first-order manner. This is why we needed these two parameters. We wanted to avoid an infinite step. So this is why we needed K and N. For every K and N, you can write a first-order theory which expresses what it needs to express. Well, put these all things together in a theory. You don't want to see how they look, what they look like. They're really horrible. But anyway, and then what? And then like Lindstrom did, yeah, you take any finite part of that theory. It has a model. Use compactness, the whole thing has a model. Oh, but then you realize, all right, I have these two chunks here. That one was a model of phi, one was a model of not phi, and on top of that, you have something that encodes bisimulation. Oh, that can't happen because phi was supposed to be invariant under bisimulations. Contradiction, end of proof. So this is our theorem. Important thing is it works for any signature F. So we claim that this is the right notion of bisimulation to use because it's modular in that engineering sense that you could sort of pick and choose. And this is really it. We also have undecidability of invariance under bisimulations, but that was expected pretty much. Nothing to write home about. And thank you very much.
Oh, Tomasz, thank you. So, questions, remarks, comments? I cannot ask a question because it's my